But it's good constructive critiquing.
No, all right, let's get started. So the readings for this coming next couple days. The new one is the Westfall, Kenny, and Ted reading. It's already posted. Also, I've already made an announcement through Blackboard, but the homework from this past week is now optional because it got posted late. There will still be a key, so if you are able to do it, I encourage you to work on it, because I want to give you practice this unit, since a couple things to do. So if you have the time, I encourage you to work on it, but it's not required. You don't have to turn anything in. For drill and homework this next week, I'm going to try to give you some of the practice that you might have missed. For drills in general, we've been transitioning over to doing more guided exercises. So that's the kind of thing that you got to expect for the next drill too. So we're continuing on with this topic of linear mixed effects models, where we've sort of made this break to new concepts, although we're still following with this, the general idea of breaking apart a data set into chunks and then doing something on chunks and then analyzing the chunks in different ways. That's the same, but of course, we saw on Monday that a few of the details are different. In particular, we have this, we have to find those individual participant effects, random effects, in a different way through maximum likelihood estimation. So some things are different. A fair number of things are different, but the general idea behind the procedure is still the same. One thing that I have not talked about so far is there's one last type of random effect that I haven't discussed at any point explicitly during this unit. And it's a type of random effect that does show up in your output, and it does kind of matter. It matters in particular ways when you're fitting these kinds of models. But in order to describe how it might matter, I first have to introduce it more explicitly. So, of course, the types of random effects that I've discussed so far are those little participant intercepts. Often they're like the participant means, but they don't have to be the means. They're just like any other intercept, just apply to one participant's chunk worth of data. And I've also talked about slopes. So those are the participant effects of quality if you're evaluating grades. So those are the two types of random effects that we have so far. There's a third type that is a little bit different from either of those. So to describe what this is, we're going to move to a new data set. I think it would be interesting to talk about something other than gradient evaluation. So that's one of the reasons I wanted to change data sets. But also, actually, I downloaded this data set from a recent paper. It's posted on the Open Science Framework. It's a pretty cool study. Thought it might be interesting to talk about that study just a little bit, just so you see like some of the types of problems that you can apply linear mixed effects models to. Linear mixed effects models are super flexible, and they allow you to ask some pretty interesting questions. So this will give you a taste of what the kinds of things that you can do. So the paper, if you're curious, is by Jesse Sun and Samin Vazir. You can look at the materials and whatever if you wish. You just have to follow that link. And what they did was they drew on a larger project that had installed a lot of people over time. And they got a lot of different measures. This is just a piece of that overall project where 248 people, they had between 5 and 20 21 data collection sessions. So a lot of points of observation. And the number of points vary quite a bit from participant to participant. Jesse Sun and Samin this year are primarily personality psychologists. A lot of what they study is the extent to which people have insight into their personalities. And one of their findings is generally people do, although there's some variability in the dimensions that people have the most insight in. What they want to know was if you stop someone at a given point in time, like this is sort of a brief window where you're doing something, do people know in the moment that, oh, I'm acting extroverted right now, or oh, I'm acting pretty open to experience? So at these different data collection times, they sent a smartphone link to a brief personality inventory. And they also had audio recordings that were taken from an iPod app. And they looked at the personality data, the people's reporting personality, like were you acting open to experience at this point in time, were you acting kind of neurotic? And they looked at the audio recordings and had them coded by other people to where they rated them on things like, this person is acting kind of neurotic right now. And what they did was they compared the people's reported assessments of how they were acting to the ratings of the audio. So that's the question: to what extent do people have insight into how they're behaving moment to moment? A pretty cool data collection method, in my opinion, really cool actually. And it's a pretty interesting question. So Ken gives you a sense of the range of questions that you can ask with this kind of statistical model.
I don't know how they did that audio recording.
It's pretty involved. So the audio recording, not coded. Yes, there's something called the, I don't remember what the acronym stands for here. It's an app that you can put on an iPod, or I think you can put it on a smartphone too. If you go to the paper, they give some of the details of how they did this. Like I said, it's pretty cool. So in this particular study, the thing that's used as the predictor is people's reported neuroticism. They also had other personality dimensions, but I'm working with neuroticism here. So it's a 1 to 5 scale, 1 is lowest, 5 is highest. Neuroticism is like, it assesses things like negative emotionality, how much you experience negative emotions, how much you tend to experience negative emotions. And the outcome is the coder's ratings of the neuroticism measured on the same scale. And of course, I already mentioned the question. So in this particular study, the question is, how much insight do people have into how they're behaving? Do their ratings match what coders think, observers think? So in order to fit this kind of model, we follow the same procedure that we've been using for all these repeated measures designs. You have a participant level model. You're breaking apart the data set into chunks, applying a statistical model to the chunks. And in this case, we've got an intercept for each participant and a slope, which is the coefficient for people's reported level of neuroticism. What's new, which was also new last time on Monday, is the fact that these participant level estimates are estimated with error. We have an error term. So this is just showing one person's data, their comparison of their reported neuroticism with the coded neuroticism. Of course, we're doing this many, many times across all the participants. And for each participant, we can get an intercept, which we have here at 0 off the graph, and a slope. One thing I want to point out here is that, of course, depending on where we are for this participant, so whether we're at 1, this is the created mean, the overall mean, or 5, depending on where we are, our intercept is going to be different. So if we took this participant's data, subtracted 1 from all the points, then went through this procedure, we get an intercept down here. We subtracted 5, went through this procedure, we have an intercept that's a little bit higher. This is true for all the models we've looked at that allow a slope. One thing that the slope allows is for the intercept to be different depending on where you are in the model. Is that familiar? Does that make sense? Where you are on reported neuroticism is going to affect this participant's individual intercept. What I'm showing you now is the results of going through this procedure and extracting out each participant's intercept and slope. So each of these faint lines is one participant's data. This is called the spaghetti plot that I've mentioned in past lectures. So it's just showing an individual prediction line for each participant. And this is our overall prediction line. I use that term fixed effects. This is the prediction line using those fixed effects, the overall effects. So let's consider one part of, or one point along reported neuroticism. So this right here, the 2.2, that's our overall mean neuroticism score. And I notice that each participant has a point at which their line intersects with this vertical line. So there are a bunch of individual intercepts at this point in the model. And I've marked each of those individual intercepts with a red dot. You can't necessarily see it because it's a little bit far away. There are also a lot of them, so they kind of overlap. But just making the point that there's a certain point for each participant where their prediction line meets that vertical line. I can take those intercepts at that particular point. So this is at the mean of reported neuroticism. And put those, or put the difference between our fixed effect and those individual intercepts along the x-axis, and the slopes for each participant along the y-axis. So what I've done here is I've taken all the y values, the intercept values that I get at this vertical line. I've taken those and put those on the y-axis. And then I've taken each person's slope, that individual participant slope, and put them on the y-axis. Does that make sense what I'm doing?
Based on that overall mean?
Yeah, at this point. So I've taken the intercept at this particular point. So this person's intercept might be 1.5. Up here at the top, this person's intercept might be 2. This person's slope might be about 0. This person's slope up here might be, I don't know, let's say it's a half. So I plotted each person's individual intercepts, those things that I extract out when I fit those little mean regressions on the x-axis, and their slopes on the y-axis. And obviously, there's a certain relationship between the distant intercepts that I get and the distant slopes that I get. Does that make sense? That's all I'm doing for now. We're not doing anything necessarily with this relationship. I'm just showing you that this is a certain procedure that I can look at, at the mean neuroticism score, what's the relationship between the intercepts I get and the slopes that I get. I can do that for other points on reported neuroticism. So this is at reported neuroticism equals 1. Notice there are a lot of different participant intercepts where each participant's prediction line meets this vertical line. And one important thing here is that it looks like each of these lines, each of these individual prediction lines is meeting this vertical line at a different place than they meet this vertical line, right? You can sort of see how the spread in the red dots is a little bit smaller here than it is here. People see that?
So you're getting the X and Y of every point when the dashed line crosses all those.
Yes.
Okay.
This is just applying that concept that I mentioned for this participant on a pretty broad scale. So for this participant, their prediction line meets this early vertical line at a certain point. That point is lower than it meets this vertical line, and that's lower still than it meets this vertical line. So I can apply that concept to everybody. And one thing to notice is just that the spread of the intercepts here is different than the spread of the intercepts here. The points at which this vertical line meets each of these individual participant prediction lines are different here than they are here. How would you about that?
I'm doing pretty good. So it seems like some people have higher reported neuroticism that matches up less well with the coded neuroticism. Is that kind of what's going on?
Or a somewhat more precise way to say it is that the spread, the difference between each individual person's coded neuroticism is larger over here than it is here. So there's greater spread from the overall mean neuroticism at this point than there is at this point. There's less coherence, I guess, between everybody's reported coded neuroticism. So, right, each participant's intercept is different at low levels of reported neuroticism than they are at high levels. And that also, we also have a different level of spread at low levels of neuroticism and at high levels of neuroticism.
What exactly do you mean by each participant's intercept?
I mean, you take one of these little hair-thin lines, you trace it along, and there's a certain point at which the hair-thin line meets the dotted line.
Well, isn't the intercept when it's at 0? Like, aren't the dotted lines just like a point on?
Yeah, so I guess I haven't been changing this axis. Let's imagine though that I took every participant's points, all the data, subtracted 3, and then redid the model. That would put everybody's intercepts at 3 3 on reported neuroticism, or let's say I did it with 2.2. That would put my individual participant intercepts would be interpreted at the mean of reported neuroticism, and the y-intercept would be this point.
Right, but I guess I'm just confused, like, it seems like the intercept will always be different depending on how you center your variable, you know?
Correct.
Like with past stuff that we've done too.
Yes, yes. Only point I'm making right now is that if you choose to put the y-intercept at different points in your model, you're going to get different individual participant intercepts, and also there's going to be a different level of spread in those intercepts.
So I guess the level of spread is the only thing that's new, right?
That's the new thing, correct. Other questions? So if I took each of those intercepts at, now I'm looking at the very low level of reported neuroticism and plotted them on the x-axis and the slopes on the y-axis, that would give me a different relationship between intercepts and slope, participant intercept, participant slope. And that relationship is a little bit different than what we saw when we first started doing this. So this is the relationship at the mean level of reported neuroticism, and that's a little bit different than the relationship at the very low level of neuroticism. I can also do this at a high level of neuroticism. So I just dropped a vertical dotted line at 5 on reported neuroticism, as if I had subtracted 5 from my device data and refit the model. Notice yet again, the amount of spread that I have in those individual participant intercepts is different yet again than it is at the mean level of neuroticism or at the lowest level of neuroticism. And if I take those points and those intercepts and plot them against the slopes, once again, I have a slightly different relationship between individual participants, the intercepts, and individual participant slopes. So what you're seeing here is that that relationship between intercept and slope changes depending on where you are in the model. It's different points in the model are going to have different participant intercepts. The participant slopes are actually going to be the same at each point, but the intercepts are going to vary. And that creates a different relationship between intercept and slope. And of course, the reason that this happens is that feature that I pointed out about how the degree of spread is changing and the actual values for each participant are changing too. So the person who had the highest intercept at one point is not going to be necessarily going to be the person who has the highest intercept at another point. This relationship between intercept and slope is this last piece of output that I haven't talked about when you do a summary on the normal model. That's that correlation parameter. The way this value gets calculated isn't exactly this process I'm talking about, where you take a point, literally take the intercepts and correlate them with the slopes. But it's pretty similar to that. The reason it gets a little bit more complicated has to do with maximum likelihood and shrinkage and all this other stuff. But that at least gives you a conceptual handle on what this means. It's telling you something about the relationship between, for a given point in the model, take those participant intercepts, what what's the relationship between those intercepts and slopes.
Can you tie this back into the spread part?
Yeah, so there are going to be two things that affect the size of that correlation. One is the amount of spread in each of the variables. The second thing is whether the rank order changes. So as I was saying, it's not necessarily going to be the case that the person with the highest intercept over here would be the same person as the person with the highest intercept over here. Notice that top line is declining very steeply, and over here, the order changes. So this top line right here, it's not the top line anymore. So let me give you a sense of like how this correlation actually affects the rate of effects that you see. One way to think about what it does is it affects the direction of a fan that you see spanning out from each of these different ones. So if the fan is pointing in a particular direction, that indicates that there's some correlation between intercept and slope at that particular point in the model. So I'm always looking at 0 right here. If the fan is, or if the point at which the lines all cross is to the right, that's what a negative correlation looks like. If it's to the left, that's what a positive correlation looks like. So what this correlation does is it affects the direction of the fan. This is a little bit difficult to think about, and actually in most cases in linear mixed text models, this parameter is not something that you're interested in interpreting. It is something that's necessary to generate your rate of effect structure. So it is estimated. But it's not typically something that is interpreted. I mean, unless someone's doing some really cool project out there that I don't know of, I've never seen anybody comment on this correlation rate. But it is something that Elmer gives you. We saw that correlation in the output. And this is what it's doing. It's affecting the direction of the fan, the spread of the individual prediction lines. Another important part of this correlation creator is that if you're at a funky point in your model, so for example, in this project, the participants' reports of their level of neuroticism are on 1 to 5 scale. So by default, we're at 0, which is outside of the range of predictions. You can get kind of funky values for the correlation parameter. And actually, you can get values that just don't make sense. We've seen a couple times, and I'll show you in a bit too, that sometimes this correlation becomes -1. Well, that's why. Because sometimes when you're at a funky point in the model, you get a funky value for that correlation.
What would be a funky point in the model?
A point in the model that doesn't make sense. So you're dealing with like I said, a 1 to 9 scale and 0, you haven't centered your predictor. So depending on whether you've centered your predictor or not, the intercepts might not make sense. Or sorry, the correlations might not make sense.
because your intercept is set at 0, which
Correct.
is not
Correct. So that's something that I will come back to shortly, because this is one of the things that can make it hard to fit the linear mixed effects problem. And really, I think that's the main reason to care about the correlation parameter. I've never seen it be of substantive interest, but it can, that is one of the things that can go wrong, that you have a nonsensical correlation parameter. Yep.
So, as an interpretation of that value, is that the average change in the relationship between the slope and intercept for a given individual from one unit to the next?
So it means that as you increase a unit on reported neuroticism, the relationship between intercepts, as you increase a unit on the average level of reported neuroticism that person has, that person's relationship between reported neuroticism and included neuroticism becomes stronger. So it refers to the relationship between the intercept, the average level of neuroticism for a given person, and their slope. How you have to increase your predictions on coded neuroticism if you increase the unit on reported neuroticism. So like I said, it's kind of hard to think about because it's not directly about reported neuroticism at all. Instead, it refers to the relationship between the person's average reported neuroticism and their slope.
Yeah, so I guess depending on the question, your research, a lower number might indicate that it's a better measure throughout, and then a higher number would indicate so greater change across.
I don't think it says anything necessarily about whether the measure is better. Let me draw a couple graphs for you to see why. So let's say my fixed effect always looks like that. I have a strong relationship between reported neuroticism and coded neuroticism. The way you could shift the correlation around that, around this fixed effect is that the point of spread is either something like this, or it's something like this, or it's something like this. So it doesn't necessarily speak to the strength of the relationship. It's, and in fact, that's partly why it's often not of substantive interest. It's hard to craft research questions answered by this parameter. Might be one out there, but I haven't seen it so far. Another funky thing about the correlation parameter is that it's often not estimated with very much precision. And in general, if you're trying to do significance testing with these variance parameters, the random intercepts, the random slopes, or the correlation between the random intercepts and random slopes, you often need a lot of data. It's hard to do it with very much precision. A lot of people just recommend not doing it at all. There are ways to do it, but you need a lot of data.
Is it not similar to an interaction term?
Yeah, I suppose it is.
Variable.
Yeah, I suppose it is. The relationship between an individual person's slope changes depending on where you are. on the average level, on their average level of theory. Yeah, that's a good way of thinking about it. It's like an interaction term writ large.
So the participants here have different numbers of repeated measures for each.
Yes.
I'm having trouble grasping that because we've only dealt with consistent numbers.
Yeah. Let me go back to this person's data set. So this person has, I think it's like 14 different observations. But I could take another participant who has only 2 observations and still draw a line that has an intersecting slope. Or I could do it if they have 200 observations. Doesn't really matter. So this is one way in which linear mixed effects models are different from models where you're taking different scores. It doesn't really matter if one person has more observations than another. At all, the procedure works the same.
It doesn't matter if there's more data for somebody. Wouldn't it make the results not fair?
You do end up knowing more about people with more data, but fortunately, that's all accounted for in that maximum likelihood method. So the procedure from your standpoint is the same regardless of whether everybody has 20 observations, whether one person has 2, another person has 15, whether everybody has 100. It's all the same. I'm glad you asked that. Thank you. Other questions? So again, the main takeaway actually about this correlation parameter, I would like you to have some sense of what it is. It's the relationship between intercepts and slopes. But the other main reason we care about it is that this is one of the stress points in fitting linear mixed effects models. It's one of the things that can muck up the procedure. And the way it can muck up the procedure is if you're at a weird place in the model. So that's actually going to be the next thing that we talk about is things that can go wrong with linear mixed effects models. You may not have encountered this yet, but if you're fitting linear mixed effects models, it's a very powerful tool, but your software often complains a lot. There's a section in the one of the readings that I assigned Brower and Curtin that has a table of different ways different things to check if your software is complaining at you. I'm going to give an overview here, but I do encourage you to go back to that paper if you are using linear mixed effects models in your own research. It's a good reference. A good thing to consult if you're trying to figure out, if you're trying to troubleshoot. So the reason that stuff can go wrong so much more in linear mixed effects models has to do with how we find the best estimates of the R random effects, one of which is that correlation parameter. So I mentioned on Monday that one thing that makes linear mixed effects models different is that you have to use this procedure of maximizing the likelihood in order to find those best estimates. So back when we covered generalized linear models, I introduced this idea of finding the specific parameter values that maximize the probability of observing your data. I used that coin flipping example where you can try out a bunch of different values for the probability of getting heads. One of those is going to fit your observations best. That's what's happening here too, except that it's applied to our random effects values. The math of how that happens is kind of complicated. It actually, there's not like a direct solution that you can apply, like, it's not like 2 plus 2. Instead, it's literally cycling through a bunch of different parameter values to find the ones that maximize the likelihood. It's an iterative procedure. And with linear mixed effects models, more than any other model that we've encountered so far, sometimes that program that's cycling through all of these different parameters gets stuck. That's called a failure to converge. But other problems can happen too, like software for linear mixed effects models complains a lot. This is actually generally true as you get to more and more complicated models. So if you ever take a class on structural equation modeling, you're going to encounter this problem there as well. The more complicated your model, the more constraints that has to satisfy in order to give you the best estimates, the harder it is to find those best estimates. So this is not just true of this type of model, it's also true of lots and lots of other statistical models that are a little bit complicated. I'm giving you a reference here for another reference actually besides the Brower and Griffin paper that describes things that you can do to get your model to work well. Just follow this link. It's the reference was written by Ben Volker, who was the person who wrote the LM4 package, the one that we're using. I end up using this reference a lot too, so that's another place that you can go. So let's go through some things, some ways that you can troubleshoot. One way is a little bit obvious, but you can check your data. We have that unit on checking data integrity, like maybe you have one person who somehow has a score of 99, you're using a 1 to 9 scale, which just doesn't make sense. There's a transcription error or something. If you have really unusual values in your data, or values that are just don't make sense, that can muck with the optimizer that LM uses to find those best estimates. That's actually a feature in some ways of linear mixed effects model in this case, because you're having something complain at you instead of just like mindlessly going through the statistics and working with estimates that are wrong. But anyway, that's one thing to check. Make sure that you've cleaned your data set, that there's not something like horribly wrong or off about your data values. So that's an easy one. I'm going to go through ways to come up with to make things right in sort of order of preference. So this is at the top because you're finding a problem that you want to fix anyway. So fixing the problem is actually going to help you in general. Now I have one solution at the bottom that you can sometimes use, but I in general I'm going to recommend against it if you can help it. The next thing you can do is check the code. Have you is your model, have you used the right formula when you made the call to open? Is there a bug somewhere in your code? That's another thing that can cause your optimizer to complain. So again, fixing this kind of problem is a good thing. You don't want to be running code that's doing something different from what you intend. The next thing that you can do is change optimizers. It turns out that because this is kind of a complicated problem, finding those maximum likelihood estimates, the best estimates, there are a lot of different programs that implement different ways of finding those best estimates. Those programs are called optimizers. I think I've used that term back on Monday. The way you do that, the way you do implement much of these solutions is you work with this parameter in the call to Elmer called control. You've seen that way back when we first started using Elmer. I didn't describe in detail what it does. Well, now I'll tell you what it does, or some of the things that it can do. These are basically ways of either choosing optimizers or changing what the optimizers do. So everything I'm going to show you goes in the parentheses after Elmer control. These are all options that you can choose for Elmer control. One thing you can do is change the optimizer, as I mentioned on this bullet point. The one that Elmer uses by default is called the Bobbyca optimizer. I don't know why it's called Bobbyca, it just is. But I have encountered situations where Bobbyca does not find the best estimates. Elmer complains to me. So you can change that optimizer, and sometimes you find an optimizer that does give you the best estimates. There are a bunch of them in this package called opt-in-x. If you want to choose one of those optimizers, you say optimizer equals opt-in-x, and there are other things that you can modify in Elmer control that tell you, okay, I want this optimizer from opt-in-x, or I want this other one. If you want to know the details, you can consult that, some of those resources that I'm giving you. I'm not intending for you to know, or I'm not trying to cover in detail what to do in every case. What I'm trying to do is give you some resources that can work things out a bit on your own. Or at least you know where to go. Another option is this package called NL opt wrap. It's called NL opt wrap because it's a bunch of other optimizers that are written in a different language that were ported over into R. This is a wrapper for those, it's called a wrapper. It's just a way to access those optimizers now. All the optimizers under NL opt wrap are in the NL opter package. There are other specific things that you need to modify if you want to use one of those optimizers. Again, you can consult that posted by Ben Volker. Go to the documentation for NL opter. A couple of things that you can do if you're interested and want to do this. Finally, there's a bit of code that you can use. GitHub, I think I mentioned in the data integrity section, that's a way to, a lot of software developers use that to post this code. If you type all this stuff into R, you'll download a bit of code that allows you to try many optimizers at once. It's called allfit. So if you run this bit of code, you'll be able to try a bunch of optimizers at once. The reason that this is a good option, maybe slightly less preferable than actually finding an error, is that if you change optimizers and new optimizer works, those are still the best estimates. I mean, it doesn't matter so much which algorithm you use to get there. They're always going to be the maximum likelihood estimates if you find them. So you're going to be finding the right answer, the answer that you want, the maximum likelihood estimates. It's just that you're tweaking the method that you use better. Sometimes there's one method that works better in a specific situation. Sometimes a different method will work better. So this is a pretty good option. There are also a couple things that you can change within Elmer. So this isn't changing the way that you get the best estimates. These are changes, sort of hacks that you can use in Elmer to ignore certain warnings, or you're basically saying, okay, I know you're complaining, but I want you to find the estimates anyway. The reason this is less preferable than the other options is that those warnings are often there for a good reason. So you ignore them at your own risk. So there's certain things that you can do to say, I know you think that we're going down the blind alley, but I want you to go anyway. So not a great option most of the time, but sometimes it's okay. One of these warnings that we had already turned off, even though I didn't mention it, is this parameter called check.nops.versus.nre. What this is doing is it's saying, okay, I see that you're in a situation where the number of random effects that you're extracting out for each participant is equal to the number of observations that you have for each participant. And it's saying, do you really want to do that? And we already saw that sometimes we might want to do that if we're dealing with a model that could be represented as like a series of different scores. So, the first, in Unit 6, when we first started talking about repeated measures, we saw that when we have these situations where we're getting out as many pieces of information from each participant as we have observations, we can represent that as a series of different scores, or we can use Elmer. If you're using Elmer, you have to turn this on. And that's perfectly legitimate, that's fine, it'll give you the right answers. There are cases where you might not want to do that, which is why this is built into Elmer. But there are cases where you can turn it off and nothing catastrophic will happen. This isn't exactly a fix per se, but it's something that you might want to do if you're trying to get a model to fit and you're having trouble and it's taking a long time. What calc.derivs does is Elmer does a whole bunch of checks once it's done finding some best estimates, the maximum likelihood estimates, or what might be the maximum likelihood estimates. And what those checks do is it's basically a way to see these really maximum likelihood estimates, or is there something funky that's happening with our model? That process takes a long time, a lot of computer time, and sometimes these models can take legitimate computer time to fit. So if you're trying a bunch of options just to get something to work, you can say calc.derivs equals false, and it'll save you computer time. This is an option that I've also done this without saying exactly what it does. It's just a way to make things run faster. You often want these because you want to be warned if something might be going wrong, but there are certain situations where you might not. Another thing you can do in addition to fiddling with Elmer is change some options within the optimizer. This is perfectly fine to do. What exactly you do really depends on which optimizer you're using, whether it's the default one, the one called Avica, or some other type. What exactly you do is going to vary from optimizer to optimizer. The way you do this within Elmer is there's this option called opt control, optimizer control, and you give it some stuff. The one that I've messed with, and that is a reasonable option to mess with, and that will generally be true across most optimizers, is each optimizer. So what's happening under the hood is the optimizer is changing those estimates for the random effects until it finds the estimates that give it the highest likelihood. And it jiggles around those estimates and then calculates the likelihood and does that many, many times. This controls how many times it does that, how many times it jiggles around the estimates. So sometimes you can change this to kind of a high number. It'll run on your computer for a while, but eventually the optimizer finds the maximum likelihood estimates. You just give it a bit more cycles and it does its thing and things work out. This is actually a fairly good option. Maybe it should be number 4 instead of the other one. Because if this works, then you're good. Those are the maximum likelihood estimates. Most likely. The last one, and the one that you may not want to, well, often you might not want to do unless you have to, is actually change stuff about the model that you're giving to Homer. And the reason that this is generally the least preferred option is that many of the things that you can do here might actually give you the wrong estimates when you're changing your model. Maybe that model is wrong. One that's pretty reasonable is something that I've already hinted at, which is centering, or, oh, I haven't hinted at this one yet, but one pretty reasonable option is changing the scales of some of your variables. If your variables are on very different scales, so let's say that you're looking at the relationship between a reaction time measure and a 1 to 5 scale. So if your reaction times are measured in milliseconds, you might be dealing with numbers in the hundreds or even the thousands. Whereas your scale, your self-report scale, might be all 1 to 5. If the scales are really different, sometimes it mucks with some of the optimizers. This hasn't often been a problem for me, but it does come up sometimes. So one way that you can change your model without changing the meaning of the model too much is to, say, divide that reaction time measure by 100 to get it on a similar scale as your other measure, your self-report measure. Oh, I guess I forgot to add this bullet point, so I'll change this on the slides, but another option that I have hinted at is centering your variables. Centering your predictor variables. So what that does is it might change that correlation parameter to something that makes sense or makes more sense. And that can sometimes fix some of your problems. Sometimes your optimizer will complain because the correlation parameter is something that just doesn't make sense. So yeah, I'll add that. I just forgot to add it onto this slide. The last one, and the one that you generally ought not to do, but sometimes it's an okay option. Actually, there's some methodological debate about this. So I think you generally ought not to do it, but there are people who offer to say that it's reasonable. So it might be defensible reasons to do it, is just not estimating some of those random effects terms. So in all the cases that we've worked with so far, we've always estimated all the random effects that we could. So if we're dealing with the relationship between self-reported neuroticism and rated neuroticism, we estimate an intercept for each participant and a slope for each participant, and we've also estimated that correlation between intercepts and slopes. But there are ways to tell Homer, I don't want you to estimate one of these random effects. And that's what this means. We're basically assuming that everybody, there are no substantive differences between people in their average level of neuroticism. Everybody has the fixed effect and then some totally random error around it. That's what we're doing here. And what this can fix is cases where, say you have a result like this where the correlation parameter is 1. What this means is that the optimizer couldn't find a good solution. So it's just giving you a 1. This is okay, actually. You don't have, this isn't something that you necessarily have to fix unless it gives you a warning. But in a situation like this, it could be reasonable to just say, you know what, I'm not going to estimate this from my data. I'm not going to give people, I'm not going to assume that these intercepts and slopes have this correlation. I'm just going to give everybody the same relationship between intercept and slope. So you can tell Elmer just not to estimate this at all. And this is one of those situations where sometimes omitting some of these terms allows the optimizer to converge on a solution where it couldn't perform. The most common term to remove is that correlation parameter. Most people believe that removing the correlation parameter doesn't have any necessarily huge negative effects. So this is where I start if you're going through this list and you're at the bottom, you're still trying to get your model to converge. I remove that correlation parameter first. The way you do that in the formula is through this double bar right here. The second thing that you can do is remove the random slope for each participant. This is where I go next, but here I think most people argue that you're starting to get into danger zone. The risk, if you remove the slope, is that you can have false positive results. So you can say that there's an effect where there really isn't. That's generally what most people think happens if you're down at this point in place. I'll give you a reference that talks about this problem. And actually, with this last option, removing random intercepts, the costs can be quite large. So normally we like alpha for a false positive rate to be at 0.05 or something like that. If you're making a mistake here, the true false positive rate can get up to like 0.20 or sometimes even higher. So that's why I think it's not good to go down this list too far, because when you're down here, you might be making pretty severe mistakes. The reference that I'll give you that makes this argument is this paper right here. That's just a good reference to keep in your back pocket. The argument that these researchers make, Dale Barr and colleagues, is that you should always add in the most random effects that you could. That's what we've been doing before I even introduced this idea of not doing that. So by default, you ought to be figuring out, which of your variables varies within people, and then add in all the random effects for that little participant model. That's what you should do by default. And that's the argument that these people make. But like I said, there is some debate about this issue. So this isn't the only opinion out there. If you're interested, well, start with reading this Barr paper. I believe there are some papers by Ben Volker, and it's very technical, and unless you're super into like the nitty-gritty details, it may not be important for you to be that familiar with it. But I do want you to have this reference, at least, for why it's good to add in all those random effects. Questions? So the reason I'm bothering to go through this at all is that these issues do come up. Like this is a problem that you'll face if you're using linear mixed effects models. And actually, I think a lot of the questions that social scientists are interested in involve random effects, involve looking at units that have some sort of dependency on each other. So I do think that this is a problem that you'll encounter. Again, this is a good, practical list of steps to take that can get you the estimates that you're interested in. I just wanted to show you that often removing that correlation parameter at least doesn't necessarily affect things that much. Removing the other parameters can. But here are two graphs, one with the full model that we started with, and one where I've removed the correlation parameter. You can see, it's even hard to see, but there's a little bit more spread out here in this model at the extremes than there is over here. Didn't actually make that much of a difference. This is often the case. That's why this is the one parameter that I think is most acceptable to remove, at least. And if you get your code in R, you'll see, well, one, if you remove the correlation parameter, you just don't see it off to the right over here. But two, the other random effects are pretty similar. So the random slope is a little bit different across the two models, but it's not that big of a difference between these estimates. If you look down to the fixed effects, again, there's a slight difference, but not a huge one. If you use capital A ANOVA to get your p-values, the p-values will also be pretty small. So not a huge amount of difference. That is often the case. All right, so we talked about this last type of random effect, correlation between intercepts and slopes. The way to think about it is it tells you the relationship between the average level for a given participant and their responsiveness to whatever manipulation or other variable that you have. It's kind of hard to think about, but one thing that it controls is the direction of spread of your individual physical lines on that spaghetti. Another odd thing about the correlation parameter is that it's going to be different at different points in the model, and that's how it ties into this problem of fixing issues with your models. That's one of those things that you can modify to actually get your optimizer to do the thing that you want. And then second, we talked about sort of these nitty-gritty practical things that you can do to actually do the work of fitting these models. There are a couple obvious ones that you want to do in any case. Check the code, check your data, check it for integrity, make sure that there aren't any egregious errors. The things that are a little bit more specific to linear mixed effects models are things like changing your optimizer, fiddling with the options in Homer, fiddling with the options for the optimizer. And the least preferable case is actually changing your model substantively. If you're going to change your model in any one way, the one way to do it that's most people would think is acceptable is removing that correlation between your acceptance level. So next week is going to be our last week of new content. We're really heading up towards the end of this class very soon. Next week, we're still gonna be talking about linear mixed effects models. I'm going to add one extra layer of complication. This is probably gonna be, well, it's one of the more complicated topics that we'll talk about. I also think, though, that it matters a lot for a lot of our research, and I'll describe why next week. So it is a little bit more complicated. I've given you a lot of extra readings because I'm not expecting you to grasp all the details just in 1 week. It's more of a thing that you can get a survey of and have some resources to read up on it if it happens to be relevant for your research. That'll be the last week of content. So I'll see you all on Monday, and have a good drill.
It's 1 minute.